Alright, so welcome to another video. In this episode, we are going to look at Leibniz Rule or Leibniz Integral Rule, the Leibniz Integral Rule, or what we called the differentiation under the integral sign, which combines differentiation and integration at the same time. So this rule allows us to differentiate an integral when the limit or when the integrand depend on a variable, right? So it's basically a rule that helps us when you have both differentiation and integration at same time. Leibniz really helped in calculus. So now, this is the rule. This is the rule right here. When you have a function under the integrand, right? Both differentiation and integration, that is where we apply this rule. Now, if this rule, the first term over here, is integrated, right? The first term integrates the partial derivative. We use the first term to integrate the partial derivative of the function, which is the f of t and x, right? So f of t and x are the functions under the integrand, right? So the first term is used to integrate those functions, right? So, and the last term, which is this, is used to account for the changes in the limits. So this right here, we use it to account for the changes in the limit. And this right here is used to integrate the functions, integrate the partial derivative of this function. It's used to integrate the partial derivative of this function, the f of t and x. Now, we have some special cases. In the cases where the limits are constant, in the cases where the limits are constant, this is what I mean when you have this limit integral is from 0 to 1. This limit here is a constant. This limit here is a constant. Then, if the limits are constant, the a of x and the b of x are constant as we have here, 0 and 1, then what we will have is that their derivative are equal to 0, right? So their derivative will be equal to 0. So when you have d of a, the x, right, should be equal to db over the respect variable, which is x, should be equal to 0, right? So when you have a constant limit, their derivative should be equal to 0. And that is the special case that I was talking about. So when you simplify those formulas, then you're going to have partial d with respect to x, right? Then you integrate over the limits, right? You integrate over the limit a and b, right, of the function f of t and x, of the function f of t and x, right? So that is the simplified formula over the function f of t of x with respect to dt, right? With respect to dt. And this can be written as from A to B, you bring the partial inside because you are going to integrate the function under the integrand partially, right? So this right here, you integrate it partially with respect to the function under the integrand, right? So we have partial derivative of the function with respect to x times dt, right? So that is the simplified formula. This is how we go by the Leibniz Integral Rule. So this formula simply means that we can swap the order of the differentiation and then the order of the integration under certain conditions, right? So under certain conditions, we can swap the order of the differentiation and the integration. This means that, you see, I was having partial ds over here, but I swapped it to send in this side and bring the integrand outside. So that is what I mean. You can swap the order of the integration in this instance. So let's look at a problem. Let's look at a problem. So for instance, when you have the integral from 0 to a, I of a is equal to the integral of from 0 to 1, right? X power a minus 1 all over ln x dx, right? So this is the problem you have at hand. How do we tackle this? Now, this right here, it's with respect to a. First, when you have it, you have to consider what you have right here. So you differentiate partially with respect to a first, right? So you differentiate partially with respect to a. So differentiating partially with respect to a, you have partial of a, right? Here, partial with respect to a. Then the integral from 0 to 1, x power a minus 1 over ln x dx. So here, because it's in that form, you can swap the order of the integration and the differentiation. So we have I prime of a is equal to the integral from 0 to 1, then partial d dA s squared minus x power a minus 1 over ln x dx, right? So here, you differentiate what is under this integrand partially, differentiate it partially. So with respect to a, of course, so you know that the differential of s power a minus 1 over ln x with respect to a, right? You're going to have, with respect to a, means that the rest of the items over here are kept constant. So here we are going to have x power a ln x. Of course, you know that x power a is the same as e power a ln x. All right, so if this is like this, then the partial derivative of it will be equal to this, right? So we have I prime of a is equal to the integral from 0 to 1. Now the partial derivative of this is x power a ln x. So we have x power a ln x over ln x dx, right? So we have this taking of this, so we have partial I of a from 0 to 1 x power a dx, right? So now what we have right now, we can integrate it back, right? So now integrate it back to have the I of a, right? So integrating both sides, right? Integrating both sides, we have I of a will be equal to the integral of x power a will be equal to x power a plus 1 over a plus 1 under the limit 0 to 1, right? Plus a constant of integration right here. So here, what we do next is substitute the limit, right? So putting in the limit, we have x, which is 1, right? So we have 1 power a plus 1 over a plus 1, right? Minus, of course, 0 of everything is still 0, so we have plus our constant of integration, right? So here, we can say that our I of a is equal to our I of a I prime of a is equal to 1 on a plus c, a plus 1 plus our constant of integration. So here, because we are having I prime of a equals 1 over a plus 1 plus c, we have to reintegrate so that we can have our I of a, right? So here, integrating both sides, this now takes this, and then we have I of a is equal to the integral of 1 on a plus 1 is ln a plus 1 plus our constant of integration, right? So here, we can name this as our equation 2 and name this as our equation 1, right? So now, once we have this, then we can go ahead and say that if I of a, or if a equals 0, then I of 0 is equal to 0, right? So if I of 0 is equal to 0, then it means that we can do that same here. So if a is equal to 0, then putting that into equation 2, we will have I of 0 is equal to ln into 0 plus 1 plus c, right? Then we can have I of 0 is equal to ln 1 plus c. And we know that ln 1 is of course 0, right? So we have I of 0 is equal to 0 plus c, which means that our c is equal to 0. So if our c is equal to 0, then we can substitute that into equation 2 and find our I of a. So our I of a is finally equal to ln into a plus 1 plus 0, right? So we can boldly say that finally our I of a is equal to ln into a plus 1 plus 0. So this means that our I of a is equal to ln into a plus 1. Right? So that is the final solution to this particular problem. Ladies and gentlemen, thank you very much for watching. I really appreciate your time. Don't forget to press on notification bell, subscribe, and I'll give you more content. Bye.